Steve Dinan's been hacking car computers for 30 years, so he knows a thing or two about what they do and how they do it, and he's got no problem sharing.
I'm Steve Dinan. We're in Dinan Engineering's headquarters in Morgan Hill, California. I started working with ECUs back in 1982 when BMW first put a digital engine management system on the 325. It had a 4K chip in it, 4K of memory. And you know, basically they replaced carburetors and distributors with a computer. In order to tune the engine, we had to be able to get into the software. So we were in the Silicon Valley, we hired a software engineer and we hacked the chip. We didn't know anything about it in the beginning, and the computer science guy knew something about software. It's in hexadecimal like the current ones are. We didn't know what functions were and what they did, and there was no encryption back in those days. There was no checksum back in those days. There was no fault diagnosis back in those days. So we literally took half the chip and changed all the numbers by 10 and put a timeline on the car and said, oh, the timing didn't change. And then we changed the other half by 10. Oh, it did. And then we cut it in half again and cut it in half again until we wound up with one string of numbers like, oh, that's the ignition timing. And then we did the same thing with fuel. And that's how we found the first two maps. The first one was literally trial and error. And it was fun. An engine is basically an air pump. And an air pump is only efficient at 1 RPM. The size of the valves, the size of the ports, the size of the intake runners, the length of the intake runners, the exhaust runners, it all comes into harmony at 1 RPM. And that is where the engine makes peak torque. So if we were to look at a torque graph on an engine that doesn't have variable cam timing, it always looks like this. Okay? That's where the engine's efficient. And the valves and cams are too big for this, and they're too small for here. Okay? If this is 7,000 RPM and this is idle, okay, I'll turn this around. Then it's too small at 7,000 RPM and it's too big at idle, and it's efficient right here. Okay, so what we can do then is we can do things to compensate for it. So let's say we have ignition timing. Normally you have a distributor with advanced ignition timing. What we do is we actually advance ignition timing a little bit too much to compensate for the weak power here. Then as we build peak cylinder pressure, it wants to detonate, we retard the timing a little bit. And then as it loses power, we advance the timing a little bit. And what this does is, this takes our torque curve and does this to it. The peak is still the peak, but we're able to flatten it out by improving both ends. That's what we can do with engine management. And then we add cam timing, we can do even more. So now we have cam timing that can be altered down here and down here. And once we add cam timing in, we can take the power curve and we can do this again. And now we even get more peak torque with the cam timing. And we can flatten out even more. Okay, so what all these controls do is compensate for the fact that basically the engine's only right in one spot. When we used to jet a carburetor, we would tune the carburetor for that spot. We tuned the distributor for that spot and everything else was wrong. Okay, that's basically what we used to do back in the old days when I was young. Okay, so what we're really trying to do with the ECU is we're trying to do this, and then by adding variable cam timing, variable valve lift, drive wire, throttle, turbochargers, we're trying to accomplish this. It's impossible to do. If you look at a modern BMW, they come up, the torque levels off, they go to about 5,500 RPM and they fall off like this in the top end. So they've achieved this for probably 4,000 RPM of the power band, which, you know, when I was a kid, it was in one spot. So we've widened it from basically a 500 RPM window to a 4,000 RPM window with engine controls. Your spark plug ignites a molecule of fuel next to it, and that heats up, and that ignites the molecule fuel next to it, and it heats up the one next to it, and it goes across the combustion chamber as a wave, and it pushes the piston down. It's like riding a bicycle where you come over the top of the pedal and you lean your body weight into it to get the most amount of acceleration. We want this cylinder pressure to occur at the proper mechanical angle. So just like if you lean into your bike when you're at the bottom of the pedal, the bike doesn't go anywhere. If you lean too quickly, the pedal will come back the other way. We want to get right where we have the most amount of fulcrum on the pedal. So what we're trying to do is we're trying to get the flame propagation to accelerate and hit a peak cylinder pressure right when the connecting rod angle and the crankshaft angle is at the optimal mechanical point. That's what we're trying to accomplish. When you have a higher octane fuel, it burns slower. Okay, so if you have a low compression engine, a lower octane fuel might actually get you better performance. But with a modern turbocharged engine, we're almost always octane limited. Almost always more is better. Because we're retarding the time to the point where we're down past the mechanical advantage, we have to, just to stop the engine from detonating because the quality of the fuel is so poor. And the car manufacturers, in order to get gas mileage up, are raising the compression. So when you're not on boost, the gas mileage is up. And now the engine detonates more and they have to retard the timing more, and we're at a less optimal angle on the crank pin for maximum torque. If we add octane, we could advance the timing. And if we advance the timing, that mechanical device becomes more efficient and we gain power. So natural aspirated engine, you can certainly have too much octane. On a turbo engine, you probably can't. A typical BMW will gain 15 to 20 horsepower between race gas and pump gas on a standard tune. If you have a turbo, you can raise the boost, software works. But if you have a natural aspirated engine, these chip tuners are all claiming, 20, 25 horsepower. It isn't there because with a NOx sensor, the manufacturers are tuning the most amount of ignition advance and the ideal mixture into the engine. And they'll rely on the NOx sensor to solve the problem if you put low octane fuel in the car. So there's no reason for them to back it off anymore. But still, there are people today, there's chip tuners selling by the thousands all over the country with natural aspirated engines claiming they're making 20, 30, 40, 50 horsepower software, and it makes this much. Don't waste your money on software unless you have hardware. Now, if you have hardware like intakes and exhausts and headers, the engine has to be recalibrated for the hardware to work properly. That's the other thing people don't do. They put hardware on and they run into drivability problems because the fuel mixture and ignition time, you're not matched to the hardware. So that's important. But just software in and of itself on an NA motor doesn't do anything. It hasn't done anything since the 90s. The reason I love racing is everything else in life is, look, we can have an opinion to what I did a good job. Do you like my car or not, right? And some guy could not like it, and some guy could like it a lot, right? But when you cross the finish line, first all the opinion's gone, isn't it? There's nothing else in life that I know of that's that finite of a grade, right? You can like a movie, you can like a certain type of music, you can even like a car. But either you finish first or you don't. And I like that grade. I win a lot, and I like winning. I like the competition, and I like the grade. Race cars, in a lot of ways, they're simpler than street cars because there's only one goal, and that's the lap time. If you look at a modern racing grid, the first 10 cars are within the same second, but the average speed is 130 miles an hour. How you win a car race is, instead of finding one magic bullet, you take 100 things and you find 100th of a second. And then in the end, you're a second faster than the guy in 10th place. But you have to do 100 things. You asked about mapping ECUs for race cars. You know what we do, and one of the reasons we won a lot of car races is we actually map a race car like it's a street car. I know that sounds a little shocking, but most people building racing engines, they tune for wide open throttle. And then they fill in all the rest of the numbers so that the mixture is kind of close. And as long as the drivability is not bad, not creating a flat spot or any detonation because the calibration is off, they consider that to be done because they don't really care about emissions and drivability. But you have to realize, every time you lift off the gas, get back on the gas, if the calibration of the fuel mixture is where it needs to be, you're wasting fuel. And in the middle of a corner, you're going like this constantly to balance the car as a race car driver. And at the end of an entire hour stint, those little teeny adjustments can be a lap. And if you make 10 pit stops in a race, that's 10 laps of mapping every load and every RPM of the engine. So we run all the light load, idle, and the pits and everything really lean, just like you would a street car trying to make an emissions test or a gas mileage test. The best we possibly can. We spend hours and hours and hours on it, okay, just to get that one more lap out of the race car. Years ago, device manufacturers like Bosch was making ABS, and people making infotainment systems, and were all on different buses and different communication protocols, and every car company wanted to do their own, and the device manufacturers go, uncle, I can't make 100 different of each device, right? So you guys all got to get together and decide what we're going to be on. So they got together, I don't remember what year it was, 10, 15 years ago, and they arrived at a standard communication protocol that they could all share, so that when Bosch made a device, they could sell to Mercedes-Benz and to Porsche and to BMW and to Audi, and they could all work on the same system, and they didn't have to make so many devices. So that's now FlexRay, and it's a much faster bus than CAN. All the new ECUs, they compare the wastegate frequency to the fuel pressure, to the air mass meter voltage, to the manifold pressure voltage before and after the throttle body. And if they all don't sync, it sets a fault and says implausibility or tampering fault, because it knows you've tampered with the signals. Because what most piggyback boxes do is they modify the manifold pressure sensor, lie to the computer that the boost is low, and then the computer raises the boost back up to its target. But in the process of doing that, it flows more air and it flows more fuel. The wastegate frequency changes on the frequency valve controlling the diaphragm and the wastegate, and the computer can see all those things changing. So what they're doing now is they're writing traps to catch piggyback boxes. We're currently working on a whole replacement ECU. We just unplug the factory ECU and put ours in. To make it from scratch. And if you don't do that, you're going to be out of the car tuning business. We know that. That's why we're on it. You shouldn't tune your own engine unless you're a professional engine calibrator, because there's guys that spend 10, 20 years learning how to do this correctly, and it's not subtle. It's incredibly complicated and difficult to do correctly. People can do it badly. There's a lot of people that are doing it badly. If you want to do this as a hobby, I'm not going to drive the car every day. I'm curious about this. I want to learn. The safest way to go about it is you retard the ignition timing a whole lot, so you don't detonate the engine and break it. You make it too rich, you add too much fuel to the engine, and that's a safe way to come. That's how we started. You correct the fuel mixture first, and then you creep the ignition timing up. But you have to have some way to monitor detonation, so you have to have an in-cylinder pressure sensor or a data logger hooked to a NOx sensor, so you know when detonation is coming. Detonation occurs at 4 to 6 degrees before you can hear it. A lot of people drive around so they can hear the engine ping, they back it off. It's too late then. The detonation occurs inside the motor. It's not audible till it's ringing so loud the entire engine's ringing like a bell, and then you can hear it through the firewall in the car. But it happens way before that. Okay, so the only way to do that is you have to put a microphone on the engine, which is what a NOx sensor is, a piezoelectric microphone. Or you have to put an in-cylinder pressure sensor that monitors detonation. That's what we do, and then you calibrate the engine that way. And you have to creep up it, and you have to check every load and every RPM to optimize the cylinder pressure without detonation. It's a very complex task, and it takes a lot of special skills. And the people sell the ECUs make it, oh, you can just buy this, you can tune your engine. Well, yeah, you could if you knew what you were doing, but it's a lot more complicated than they make it sound.